In experiment 1, one group is taking an open book exam, one group is taking a closed book exam, and the difference between the means is 8.25. In experiment 2, the same experiment is happening, but for some reason the researcher can't test everyone at 10 a.m. For some reason the researcher has to test some people at 6 a.m., maybe because of a scheduling conflict. In this situation, what the researcher would want to do is make sure that the number of 6 a.m.s in group 1 is equal to the number of 6 a.m.s in group 2. That way, if the first average drops, the researcher can hope that the second average will drop by the same amount, and the difference will end up being the same as if they had tested everyone at the same time of day. To demonstrate this idea, I subtracted 10 from each 6 a.m. score. Actually, I pasted the data set over here, and then I subtracted 10 from each 6 a.m. score to account for tiredness early in the morning. Then I recalculated the means, and I subtracted the first mean by the second mean, and I got a difference. What ended up happening is the two means both dropped by the same amount, and the difference stayed the same as when everyone was tested at 10 a.m. Like I said, if the researcher does the experiment this way, like in experiment 2, the researcher can hope that this is what will happen. The researcher can hope that the difference will still be accurate. Now, in a real experiment, it's not going to work out this nicely because there's going to be individual differences in fatigue at 6 a.m. It could be that in group 1, the two 6 a.m.s aren't tired, and in group 2, the two 6 a.m.s are tired. That might happen just by chance. But if the researcher does the experiment this way, the researcher can hope that this difference will be about the same as if everyone had been tested at 10 a.m. What the researcher wouldn't want to do is do an experiment like experiment 3, in which group 1 has one 6 a.m. and group 2 has three 6 a.m.s. If the researcher did the experiment this way, what might end up happening is group 1 has one tired person and group 2 has three tired people. If that's the case, then the first average will drop, and the second average will drop more sharply because of three tired people, and the difference will be magnified. It'll become larger. To demonstrate this idea, once again, I pasted the data from experiment 1, and I subtracted 10 from each 6 a.m. score. What ended up happening is the first average dropped a little bit to a B+, and the second average dropped a lot down to a D+, and the difference became much bigger, and it's a skewed result. If a researcher does an experiment like this one, the researcher is risking a skewed result like this. A researcher also wouldn't want to do an experiment like experiment 4 because if the researcher tests all of group 1 at 10 a.m. and all of group 2 at 6 a.m., what might end up happening is the second average drops because of fatigue or tiredness, and the difference becomes more dramatic or larger. That's what might end up happening. To demonstrate this, once again, I pasted experiment 1, the same data set, and I subtracted 10 from each 6 a.m. score. I recalculated the means, and I subtracted to get a difference, and it ended up being a pretty big difference. That's because the closed book average went all the way down to almost a D-. So experiment 1 and experiment 2 aren't skewed. They're actually well done experiments. Experiment 3 and experiment 4 aren't good experiments, and they ended up being skewed results. They ended up getting a difference that exaggerates the difference in performance between the two groups. Let's move on to page 2. This is the same experiment again with an open book exam and a closed book exam. However, we don't have two groups of people anymore. In this experiment, each person is taking the exam 2 times. One time as an open book exam and one time as a closed book exam. At the top left corner, we have an imaginary situation in which each person's 2 scores are both at time 1, and actually all scores are time 1. This actually can't happen in real life because A person can't take an exam 2 times and have both scores be time 1. But this imaginary situation is a baseline or a starting point that we'll use because none of these scores are affected by practice. There's no contamination due to practice effects in this imaginary situation. In experiment 1, I have 2 people following the AB order, in which the open book exam comes first, and 2 people following the BA order, in which the closed book exam is first. When you do an experiment this way, and each person takes the exam 2 times, you expect the person to do better the second time because of practice. That's why when you do an experiment like this with 2 trials, you want it to be half AB and half BA. That way, if these two scores, if these 2 time 2 scores bring up this average, you can hope that these 2 time 2 scores will bring up this average, and you can hope that the 2 averages will go up by the same amount, and they'll get the same boost, and the difference will end up being the same as if all scores had been time 1. To demonstrate this idea, what I did was I added 10. Well, first of all, I pasted the data over here, and I added 10 to these time 2 scores to account for practice, and I added 10 to these time 2 scores to account for practice. What ended up happening is this average went up, and this average went up by the same amount. The 2 means got the same boost, and the difference ended up being the same as if as back at our starting point. So this difference is of 8.25 is accurate. It's not thrown off by practice. Like I said, if a researcher does an experiment that's half AB and half BA, the researcher can hope that the 2 means will get the same boost from practice and the difference will be unaffected, like what happened here in this demonstration. A researcher wouldn't want to do an experiment like experiment 2, in which it's 1 AB and 3 BAs. The researcher would want it to be half and half, like it is here, because if you have 1 AB and 3 BAs, then the first column has 3 time 2s that are potentially affected by practice, and the second column only has 1 time 2. And what might end up happening here is the first mean gets more of a boost than the second mean does, and the difference is thrown off. To demonstrate that this could end up happening, what I did was I pasted the data again, and I added 10 to all time 2 scores to account for practice. These 3 scores in column 1 all ended up being A's because of practice, and the average went up to an A-. It went up quite a bit. But in column 2, only 1 score benefited from practice, and this average didn't go up as much. It's still a C+, and the difference ended up being larger, and it's a skewed result. It's skewed because of practice. A researcher also wouldn't want to do an experiment like experiment 3, in which it's everyone following the same order, because if it's all BAs, what'll happen is column 1 is all time 2, and the second column is all time 1, and what might end up happening is all of the column 1 scores get a boost from practice, and none of the column 2 scores get a boost from practice, and the first average goes up, and the second average doesn't go up, and the difference is skewed, like it is here. Once again, to demonstrate this idea, I just took the original data from our starting point and added 10 to each time 2 score to account for practice, and we saw that this ended up happening. This is a skewed result. Like I said, you want it to be within subjects design like this one, you want it to be half AB and half BA. That way, the 2 columns benefit equally from practice, at least in theory, and your difference shouldn't be skewed. It should be accurate. Let's move on to page 3. Here we have an experiment in which each person is taking the exam 3 times. One time as an open book exam, one time as a closed book exam, and one time as a group exam. At the top, we have an imaginary situation in which all scores are time 1. It's just our baseline again. And this is the results here. We have the means of the 3 columns, and we have the differences. I got this difference by subtracting this mean by this mean. I got this difference by subtracting this mean by this mean. Here's the actual experiment. So if someone was doing this experiment, what's likely to happen is each person will do better at time 2 because they've taken the exam twice, and even better at time 3 because of even more practice. So that's something that needs to be dealt with so appropriately so it doesn't throw off the result. So once again, what the researcher has to do is try to ensure that the 3 columns get an equal benefit from practice. The researcher want to make sure that that the boost that each column gets from practice is equal across all the columns. And the way a researcher would try to ensure this is by, once again, assigning an equal number of people to each order. In this experiment, an equal number of people are assigned to each order because each order appears once. Well, each order contains 1 person. There's no repeats. And what I did here was I added 10 to each. Well, first of all, I pasted the data from our starting point up here that had all time 1s down here. Then to account for practice, I added 10 to each time 2 score, and I added 15 to each time 3 score to account for even more practice. Then I recalculated the 3 means and the differences, and the result ended up being exactly the same as if all scores had been time 1. So the practice effects did not skew the final outcome. The practice effect didn't skew the differences between the means, and I'll explain why that happened. In the first column has 2 time 1s, 2 time 2s, and 2 time 3s. The next column, once again, has 2 time 1s, 2 time 2s, 2 time 3s. The third column has 2 time 1s, 2 time 2s, and 2 time 3s. So in other words, each column is a third time 1, a third time 2, and a third time 3. 2, 2, and 2. That means that the 3 columns all benefit equally from practice, and the 3 averages all get the same boost from the practice effect. They all go up by the same amount, and the differences in performance stay the same. And the differences are what you actually care about. So you want them to be accurate. You don't want them to be skewed by these practice effects. And in this case, that's what ended up happening, because the experiment was done properly with an equal number to each order. Now, once again, a real experiment isn't going to work out this nicely, because it's not like every time 2 will go up by 10 and every time 3 will go up by 15, but this is what's going to end up happening in theory, and it's also what you hope will happen. Let's move on to the last page. The last experiment on the last page was a valid experiment because each order appeared the same number of times. But here, this experiment isn't valid because it's not good because there isn't an equal number to each order. There's 4 ABCs. There's 1 CBA and 1 CAB, and the other 4 orders never appear. So we have the same imaginary situation at the top, and I copied and pasted it again. And once again, to demonstrate the concept, I added 10 to each time 2 score and 15 to each time 3 score to count for practice. What ended up happening is the third column took almost all of the time 3 scores that benefit the most from practice, and these 4 scores ended up being pretty high. And this third average got most of the boost from practice. It went all the way up to almost an A+. And that skewed the results, because now the difference between these two means is much bigger. It's now a difference of 10, and it used to be only a difference of 7. If we look over here, the first column is almost all time 1, which has no benefit from practice, which is why this first average didn't get as much of a boost. It only went up to maybe a B+. So overall, one column took most of the practice effect and got a bigger boost, and that skewed the outcome. And a researcher doesn't want this to happen. The way a researcher would prevent this from happening is, like I said, by assigning an equal number to each order. So this is what you wouldn't want to do, because it's likely to give you a skewed outcome. And once again, to get this result here, I just subtracted this mean by this mean, and I subtracted this mean by this mean, and I got the differences.